We are now ready to start our next talk. Please welcome Katie Chusey, Andrew Sago, and Jesse Zhang for Pouncing over APTs for purple teaming.
All right, welcome everybody. As he just said, we will be talking about how we've been pouncing over APTs for purple teaming. So a quick disclaimer, if you do have this phobia, we will have cats in this presentation, just so you're aware. But also don't use any ideas, code, cats for malicious purposes, obviously. All right, so some quick intros. I'll start us off. I am Katie Chusey, a software engineer on the red team at Microsoft.
I'm Andrew Sago. And I'm Jesse Zhang, also a red team at Microsoft.
All right, so you guys know why you're here. We know why you're here. You probably really enjoy cats. You want to learn about purple teaming, how to build your own C2, or all the ins and outs about learning about APTs and doing your own research there. But we really want to tell you why we're here. So first off, obviously the free food, right? That's a big plus point. But really, what is the problem or the challenge that we've been facing that we're trying to solve? So we do a lot of purple teaming exercises at Microsoft. So us as a red team, we join up with our blue team, and we test their detections, and we issue our normal tactics that we do in our engagements and see if they can catch what we're doing. However, this really only helps them catch what us as red teamers are able to do, only with the skills that we have, the funding that we have, and all the tactics that we're currently aware of. So what we really want to capture and be able to test is if they can catch the external APTs and all of the actions that they would take if they were to attack Microsoft. So that's really the challenge that we've been facing in those exercises, and we'll be talking about how we've tackled that problem.
Can you explain purple team and red team a little bit more?
Absolutely, so we will get there next. So before we do that, a quick question to the audience. What is a cat's favorite color? Any takers? Purple. Good guess, it's purple. So let's talk about purple teaming. Okay, so what is purple teaming? For anyone that doesn't know, it's essentially a concept where the two sides, red and blue, to make purple obviously, come together really to share knowledge and make each other better. So if you're not aware of the two different sides, obviously the red team is issuing those attacks. They're acting as real bad guys, and they're trying to penetrate systems and find those vulnerabilities. Whereas the blue team is doing the opposite. They're looking for the attacks, they're trying to see if they can catch what the bad guys are doing, and then take action on those. What does a typical purple teaming exercise look like? We usually spin up a test environment, and us as a red team, we issue our normal tactics that we do during our normal engagements against this test environment and just act as if we were conducting a normal red team exercise. But we do it in collaboration with the blue team, and they are constantly monitoring this test environment, seeing if any alerts are fired or if they can catch anything that we're doing. And then they also get to see where their gaps are in their detections. So really the red team's ultimate goal is to improve their evasion tactics. They see where we're currently being caught, and then we can adjust for that in the future. Whereas the blue team is really trying to improve their detections and figure out where their gaps are. So our solution. How are we tackling this challenge that I initially talked about? So we've created a tool called CopyCat to try and achieve this goal. We've implemented a C2 infrastructure to help us automate everything. We've also done a lot of in-depth APT research to try and emulate the exact actions that these APTs are taking. And in that, we've implemented a lot of their tactics, techniques, and procedures. And we've also implemented a lot of our own custom modules into this tool. And we've made it very easy to add new ones moving forward. So next we're going to dive into the details about our tool, and we'll start off with talking about our C2 infrastructure and how that helps us achieve this goal of APT emulation. So first off, I just want to tell you why we're bringing up C2, why would we go into the details about our C2 infrastructure. So first off, we're already using a lot of C2, and for those who don't know, that means Command and Control infrastructure. We're already using a lot of those tools in our engagements, in our everyday work. So we're very familiar with them, and we can use them to help us achieve this goal. C2s also make it very easy to deploy binaries on test systems, so that makes it very easy to achieve those processes as well. And it makes it very easy to run specific commands on a target system and automate as much as possible. So now we'll talk about our C2.
Just gonna pull this off. Awesome. Thank you, Katie. All right, so now we're going to talk about our C2 architecture. And first off, high-level overview of it. Now, in this case, C2 is very convenient for us because C2 can stand for both CopyCat as well as the Command&Control framework. Now, for most Command&Control frameworks, you really need three components. The first component, you need the C2 server itself. Now, this is necessary because this is how the attacker is able to actually manage all the wonderful compromised systems that come back in, how the attacker is able to actually send data to those compromised systems, and also how the attacker can get data back. Now, if you look at our diagram here on the left-hand side, we have our attacker represented by our cat, and in front of the cat, we have our C2 server, which is represented by those boxes with the network stack going through it. Now, for the second component, we need some sort of way to actually get malicious code onto the system so we can actually compromise in the first place. In this talk, you're going to hear us use interchangeably payload, implant, or backdoor to refer to this malicious code. And in our diagrams here, we represent those with the email icon, the paperclip icon, and the cloud icon with the download arrow to it. The reason we do this is because based on our research, we've noticed that most APTs do utilize some sort of either malicious email, malicious link, or malicious attachment like a macro Excel attachment, or finally some sort of malicious download link in order to actually get their victims to click on it or execute the program and eventually get compromised. Finally, the third component, and arguably the most important one, is your victim themselves. Because without the victim, even the most amazing C2 in the world is useless. Like, there's nothing to target. What am I do with this system here? So in our diagram here, our victim is represented by the mouse in the middle. We've gone through the first three stages, right? We've gone through the attacker on the left-hand side, sending the payload over to our victim, the mouse. Now, unknowing to the mouse, they don't know that this is a malicious payload or malicious executable. They run the program, and alas, their system is compromised, which leads us to the far right. Now our attacker, the cat, is on our victim system, which we call either a compromised system, or during our presentation, you'll also hear us use the word zombie. So now the zombie is there, and if you look at the first top cat track in the middle, that's the zombie calling back to the C2. And now since the C2 knows that it has that zombie available to it, it can also communicate back to the zombie itself. That middle cat tracks right there is called the communication channel. And in this instance, what we're showing you is what's called a reverse TCP communication channel. Reverse meaning that the zombie actually communicates back to the C2, and TCP because it goes over the TCP protocol. Do note that this is by far not the only communication channel possible for C2 frameworks. There's also, you can run communication channels over other protocols like UDP or DNS or other protocols out there. And also there are other ways of doing it where maybe it's direct TCP, where the C2 reaches out to the zombie first, or maybe the C2 bounces through a couple proxies prior to talking to the zombie. One other thing to know about C2 frameworks is that for some of them, they also have something called a stager. And this is something that happens before the payload gets executed, And the whole purpose of the stager is to make sure that the payload has the highest chance of success on executing on that victim system. So some stagers might check for the operating system. Some of the other ones might check for what software is running on there. And some of the more advanced ones might even check for what protections are in place and then try to disable those protections prior to downloading the payload and eventually compromising the system. So now we've gone through the high-level C2 architecture. Let's go next to our tech stack for CopyCat. So we kept it very, very simple for CopyCat. For both our C2 code as well as our backdoor code, we've written it all in the Golang language. There are three main reasons why we did this. The first reason is because it runs almost everywhere. In our testing and in our purple teaming exercises, we've utilized CopyCat on Linux systems, on Windows systems, as well as on Mac OS systems. And it's worked amazingly well for us. The second reason why we chose Golang is because it's simple-ish. The reason why I say that is if you have a little bit of background in most programming languages, it's fairly easy to pick up Golang. And finally, the third reason why I chose it is because it's fast, which is phenomenal for our purposes. Now, as many of you may have read our talk's description, we did promise to show you how to build your own C2. And here is the recipe. And as with all good recipes, you need to have your ingredients and you need to have your directions. Now, in terms of the ingredients, we have three main ingredients for our C2 framework here. First ingredient is a TCP listener. Second ingredient is an infinite loop that's constantly listening for connections. And the third ingredient is a thread that gets spawned for each connection that comes in to actually handle each of the zombies that are communicating back to our C2. In terms of the directions, first off, we want to read input from standard_in/WSS. Then we're going to bake the command a little bit, give a little love, right? In essence, what we're really saying is we want to see if the command whether or not it's supposed to run through shell or cmd.exe. And also, we want to check to see if the command itself is something that's built into the C2 and something that the C2 should be doing, or if it's something that should be sent off to our zombie and be executed on the zombie system. Finally, we actually have to send the command off to our zombie, and eventually we need to be ready to receive whatever data the zombie is going to send back to us. Now, this is just a high-level overview of the recipe. Let's dive a little bit deeper. So for our first ingredient here, we have our TCP listener, and we are utilizing the GoLane net package in order to do this. So if you look at the code here, net.listen will open up the port, the relevant port that you specify. The next ingredient that we have is the infinite loop. We obviously don't want to just open up the port and then just let it close. We want to make sure that it's constantly open so that it's constantly ready to receive connections as those zombies come in. And we also include a helpful message towards the bottom that tells us once zombies do connect in, it says, hey, the zombie is connected, you're ready to do whatever you want to do with it. And finally, we have our third ingredient, which is the thread that gets spawned for every zombie connection. Now, if you remember back a couple slides, we talked about why we chose GoLane. This really refers to two of the main reasons. One for its simplicity, and one for how fast it is. If you look at the bottom of the code there where it says go space handle client, for people who are familiar with GoLane and who are not, that's what's called a Go routine. And that right there enables concurrency and allows us to handle all the threads and all the connections that are coming in. Now, in most languages, concurrency cannot be handled with one single line of code. So that's phenomenal for our usage. Now we're going to dive a little deeper into the directions themselves. So if you look on the code on the right-hand side, the top part right there is us reading input on standard/WSS. The next part is the baking part of it. So in this instance, you'll see that we are checking to see whether or not the zombie is actually running the Windows operating system. Because if it is, we want to make sure the command, when it's run on the zombie, it's run through cmd.exe. Now, if it isn't, then just run it through whatever relevant shell, like bash or something like that. After that, we do encode these commands prior to sending them off to our zombie. Then the zombie takes it, does whatever it needs to do with it, and then we need to make sure on our C2 side, the bottom code right there, the C2 is ready to actually receive whatever data is sent back to it, and eventually display that to our users. So now that we talked about our C2 high-level architecture as well as the wonderful recipe for all of you to build your own C2 framework, let's talk about some of our APT research.
Awesome, thank you, Jesse. So we've talked about purple teaming, what really inspired all of this and inspired our goal. And then we talked about our C2, which allows us to achieve our goal. So now let's really talk about how we do our research to reach that point. Okay, so how do we find the APTs that we actually want to emulate and figure out what campaigns we're going to start looking at? So we use a variety of online resources, as I'm sure you're all aware, but we also use a lot of internal resources at Microsoft as well. We utilize our internal threat intelligence team because they are doing the threat hunting. They're very well aware of the APTs that are currently active, so we use a lot of that intel as well. And then we also use our internal security operations center, who is always looking at these alerts that are firing and looking at the detections, and they're very well aware of all these APTs as well. So once we identify the APTs that we want to emulate, how do we go about picking the actions that we're actually going to implement? So we also use a variety of online resources. Some of these do cost money, but a lot are free, so that's really awesome that there's a bunch of free resources out there for anyone who wants to do this kind of research. So we do different kinds of research on these websites, and we pull different report samples as well as code samples and pick out different actions that we want to emulate from these APTs. So how do we actually go about emulating this once we find the exact actions that we want to implement? So we have a variety of different functionality already incorporated into the tool. One would be automatic IOC, which is indicator of compromise extraction from a variety of different websites. So we have implementation to do web scraping that looks through RSS and other blog feeds to really find like certain file names that APTs are using, as well as registry keys that they're manipulating when they're doing their attacks. Next, we do a lot of manual analysis. So we pull down different APT reports, and we look through the reports, look for certain file names and registry keys as well, but also different tools that the APTs are using, domain names that they might be spinning up, or different web applications that they're using. So we do a lot of manual analysis there. And lastly, we do a lot of reverse engineering, which is really cool. We take the actual code samples that these APTs are using, and we use their exact code. We do strip out the malicious part, of course, and make it benign, but we are issuing the exact code that the APT is using. So how have we implemented this into the tool? So here's an architecture diagram to try and give you guys an idea of how we've implemented this. The cat at the top is, of course, our threat actor. And then we basically have APT profiles for each APT that we support. And that is represented by the fingerprints, because each is unique to the APT threat actor. And then within each of these profiles, we have what we call campaigns. And so what the campaigns consist of, they consist of a README file, which basically lays out all of the actions that they're going to take on a target system before you implement the campaign, so you have an idea of what it's going to do. It also has a list of tools that that APT has used, maybe custom, maybe tools that we're all well aware of that are out in open source. And lastly, it has a command file, and this is how we automate all of the actions that an APT takes on a target system. So it's basically a list of commands that will execute sequentially once you kick that off on a target system. Okay, so we talked about how we get those APTs and how we implement them, so now we'll talk about the specific profiles that we currently support in CopyCat. So the first one, it is a malicious macro campaign, and it is for the APT called Turla Dark Neuron. So we're basically just emulating their initial entry into their targets here. And they started off with a spear phishing campaign that was initially targeted at the Saudi Arabia government. So they send off this Word document, and within it, once it's downloaded and you enable the macros, a malicious macro executes on a target system. And basically what this malicious macro does is it uses cert-util to decode and execute a malicious binary. So pretty simple functionality, but it's, it makes it really simple for us to emulate this action. And this is what the original payload looks like. So that's what it decodes and executes on the system. So another part of these campaigns, what we try to do is we try to implement them, but then we also try to do our own learning and research in order to evade detections. So here are two examples of how we've done this with this particular campaign. So on the left, it is basically the macro sample, all the code that it runs. And one of the detections that could possibly fire with this campaign is just based on the file hash specifically. So what we do to change that is to make a significant code change. So all we do is we add a bunch of string variables at random places in the code, and that will change that file hash and signature so that it's not detected moving forward. So as you can see, we're big fans of Godzilla, so we've named those string variables here, and that just changes the file signature there. And then on the right, another detection that could possibly fire is on that base64 encoded payload, that signature. It might detect on the whole chunk of that signature, so one way to evade that detection is to break up that signature. So doing kind of a similar action here, we're making string variables and then we're just concatenating them all together in random places, and that will evade the detection.
All right, so Katie has shown that the Turtle Dark Neuron does the base 64. Some of you might be wondering, okay, after it does that, then the signature.exe, prior to us actually replacing that code with calculator.exe, what did it do? Well, it turns out signature.exe is the first known backdoor for Microsoft Exchange servers. And the way it does this is by utilizing what's called DLL sideloading, which essentially what it does is it creates two malicious DLLs and then replaces the legitimate ones with those malicious ones. Now, once those DLLs have been replaced, when the Microsoft Exchange server starts up, it takes those malicious DLLs and essentially the server itself is compromised. At this point in time, Turtle Dark Neuron has the capability of whatever Microsoft Exchange server can do. Read emails, send emails, delete emails, and any of those other capabilities. Now Turtle Dark Neuron wanted to take this one step further. They realized, hey, instead of running let's say a reverse TCP communication channel, why don't we take advantage of the fact that we actually have this Microsoft Exchange server? So by utilizing Microsoft Exchange Server as a communication channel, what they end up doing is they would send spam messages containing C2 commands. And then the spam mail will go to this compromised system, which understands that there's going to be C2 commands within spam messages, extracts it out, and then discards that spam message. Now this is particularly effective because from the blue teamer's perspective or from our defender's perspective, they might just see a spam mail going over the network, not realizing that it actually contained any sort of malicious commands. As Katie stated earlier, we do our own research and we do want to make sure we try to emulate this as closely as possible. But of course, we're not going to just run it and essentially compromise ourselves and have it reach back out to the attacker's infrastructure. So instead what we do is we do declaw or defame the code prior to running it through CopyCat framework. In this instance, signature.exe was written in the .NET language. And this was really helpful for us because .NET has a ton of .NET decompilers out there that makes our lives much easier. Now with this decompiler, what you can do is take the executable program and then decompile it into human readable code. At this point in time, with that code, it allows us to then take a look at all the different functions. We can look at all the ones that are particularly malicious, maybe just comment those out, or we can change the malicious code to something more benign. In this instance, we really wanted to capture, at least for this campaign, the DLL sideloading capabilities. And so what we've done is, if you look on the left-hand side, that's what the user will see. First off, the user will get a message that says, hey, we're creating this DLL related to some sort of web service. Then it's going to reach into the .NET code on the right-hand side and call the extract payload and create the first DLL. After that, then it lets the user know that, hey, we're going to create the second DLL, which is something related to this task scheduler service. And then once again, it's going to reach into the extract payload function and then create that second DLL. Ideally, as a user of CopyCat, they'll see that these two DLLs have been created. But during our purple team exercises, ideally our blue team or defenders will also notice that these DLLs have been created and something fishy is going on, and they will spin up an incident in order to go and investigate this.
Thank you, Jesse. So, yeah, as you've seen, the first two were actually focused on Windows. This one is focused on Linux, and this particular backdoor, called the WinNTI backdoor, is very popular among different APT groups. And this particular variant for Linux was discovered, I think, a couple of months ago. So what we've done, we started reverse engineering it. And as you've seen, we're actually trying to emulate using the same language that the attacker is using. For the first one, we're trying to, let's say, use VBA, Visual Basic for Applications, to write the macro. For the second one, we're using .NET. In this case, the attacker was using C. The backdoor is using C. So once we opened it in a disassembler, in this case IDA, we noticed that it had a bunch of encrypted strings. So what we've done, we've ported those strings as buffers into a C program. Next thing was to hunt for the function that does the decryption for those strings. And we found it, and then we reversed engineered the function. You can see it on the left-hand side. Quite difficult to read, so that's why we ported that to C, which, yeah, made it a bit easier. Basically, this one was decrypting those strings using XOR function. And then that's how we actually found out that they were actually APIs that were later used by the malware. So as Katie mentioned before, we also have a command file in the APT profile, and basically we're issuing a bunch of commands using the tools that we already built, and then commands that were specific for the APT group. So in this case, we're uploading the tool, we're setting the executable bit, and run it. And this is what we are expecting to see. Once we've implemented the functions that the APT group has, we are actually expecting to be blocked by a security solution on the client side. And this is a very cool thing in what we're doing, because by doing that, we're also trying to predict how the next, let's say, malware, how the next strain will look like. Because we also mimic, let's say, reusing the attacker's tools and methods and the code. And then if we can do that, we may be able to predict how they're going to attack next, what tools they're going to use. But wait, we have more.
All right, so last up, we're going to talk about our CopyCat modules. So these are the custom modules that we've built into this tool to help out with the APT emulation, but also with our red team tactics as well. So just to give you a rundown, first we'll be talking about our phishing framework that we've implemented into this tool, as well as a keylogger tool. And last, we'll talk about 2 executable tools that help with manipulating files as well as registry keys. So first off, we'll talk about our phishing framework. So it is implemented in C#. And basically the premise of the functionality, pretty common sense, sends an email to the target users that you specify with a malicious email attachment. So this will be a PDF document. And really what makes this malicious is there's a link inside of that that points back to our implant that will then connect back to our C2. And then we could gain control over a system. So why do we implement this phishing framework into this tool? So it's really a common technique used among our featured APTs. So here's some code samples for you. On the left, basically just how you construct that email. We're utilizing the system.net.mail library of C#. So at the top, you set your to and from, and these are both read in from a file. And then you construct the body, and that last chunk is how you add in that PDF attachment. And then you're sending that email off using the SMTP class. And then on the right is just some extra functionality. So we wanted to make this as automated as possible. So basically you kick off the executable for this tool, and then the only argument that is supplied is whatever malicious link is pointing back to your implant. So this is how we do this automatically. PDFs are not fun to manipulate in any language, if anyone has experience, but especially C#. So it's kind of tricky. You have to read in the PDF and then loop through each page specifically, and the way that links are recognized are as annotations. So you loop through each page, you loop through all of the links, if any that are present, and then you have to loop through those and figure out which one you actually want to replace with your malicious link. So next, we'll talk about our keylogger tool. So also implemented in C#, it utilizes Windows hooks to hook into a certain environment and detect the key presses there. It also accounts for special characters, including backspace, enter, tab, space, as well as shift. And it not only captures the keystrokes that a user is typing, but also the environment that the user is typing into. So some more code samples. On the left are all of the important API calls that this tool makes. So it uses set Windows hook and unhook Windows hook to hook into that environment to detect those key presses. It uses VK key scan to get the shift state of a key. And lastly, it uses get foreground window as well as get window text to get the environment that the user is typing in to write that out to the file. And then last on the right is just the basic premise of the functionality, all the important pieces of the code to detect those key presses. The hook callback function is what is invoked when a key is pressed, and then it returns to you a code, but you obviously don't want the ASCII code, you want the readable character. So all you have to do is cast that to the keys class, and then you'll have that character. And then on the bottom is just how I'm handling those special characters. I just have a dictionary saying if this key is pressed, this is what should actually be written out to a file.
Thank you. The next one we're going to talk about is called Implant F. And as we said earlier, we actually have automated tools that will be able to parse and extract IOCs from different reports. And one of those IOCs are the file names. So what we're doing, we have a tool where we can provide a bunch of file names, and the tool has a function which is able to get a template from the local system based on the file extension that it needs. And once it does that, it will create a file with that specific name and extension. What's the purpose here? We're actually trying to see if the EDR, the endpoint detection systems that are in place, if they are able to detect those IOCs, and we're trying to emulate that.
And finally, we're going to talk about the implant arm module. This is also written in Golang. We love Golang, right? But it's written in Golang, and it has the capabilities to add, update, and delete registry keys. Now, some of you might be wondering, why don't we just utilize the built-in regedit functionality for Windows systems, right? The reason being is that when we have this, it gives us full control over it and full capabilities to manipulate it in whatever ways we want. As you heard throughout this entire presentation, evasion is the top thing, the constant battle between blue and red, right? So if they do catch this method, it gives us the capability to go in, change the code a little bit, and try to create additional evasions for the blue team. Now, this heavily utilizes the Golang registry package. And in the Golang registry package, if you add a key over an existing key, it just replaces it. So you notice that the add and update functionality for this code is very similar. And finally, the delete code right here goes out, looks for that key, and then just deletes it out. And now we have a demo.
What you've all been waiting for. Okay, our tool in action. So as you can see, this is what our C2 looks like. We've issued the help command, which basically just lists out all the possible commands you can issue within this tool. And then we are issuing the get APT command. So this will list out all of the APTs that we currently have supported that you can issue on a target system, all the campaigns. So now the info APT command. So this is really useful. It will print out all of the actions that a campaign will take on a target system. And then next we'll kick off the zombies command. So this is basically going to list out all of the machines that are currently connected back to your C2 that you can interact with and run campaigns on. And next we will kick off an actual campaign. So we use the get APT command to do this. We select an APT as well as a campaign within that profile. And this specifically is going to run the OP Kitty campaign. And all this campaign does is generate files using that implant F exe that we just talked about on the target system, but it's naming them all in the same ways that the actual APT did, and that's where the detection should really fire, is on those file names specifically. And as you can see, it prints out very nicely all the actions that it took on that system. And that's how it works.
Now, do you want to hear a bad cat joke? Just kitten. All right. Any questions?